So what happens if we want to take the derivative of a function and it's comprised of multivariate parameterizations? And so what we're going to have to do is we're going to have to use the case 2 of the chain rule. And essentially all we can do is we can just take the partial of the original function with respect to one variable of the multivariate parameterization at a time. And so the formulas look pretty close to one another. Right? So what you'll notice is if you want to take the partial of our function fxy, which is z, with respect to the first parameter, where x is equal to parameterization of s and t, then we're going to have this formula, which just is the total differential once again, except we're using s's instead of t's, and instead of dx ds, we're saying partial x partial s, because now x is comprised of a multivariate function. And same thing with partial z with respect to the second parameter t. Right, so let's take a look at a couple examples of this. We'll notice that it's not too difficult. It's a lot of bookkeeping, but it's not all that again, it's not all that difficult. So we have our function z, x squared plus xy plus y squared, and x is the parameterization. It's a multivariate parameterization s plus t, and y is equal to a multivariate parameterization s times t. So let's find four things. Let's find the partial of z with respect to x first, and that's going to be 2x plus y. Let's find the partial of x with respect to s, and again we're just finding partial z partial s first. So partial s x partial s is really easy, that's just 1. Partial z partial y is going to be equal to x plus 2y. Partial y partial s is easy, that's just t. And then finally, for our total differential, we're just going to multiply, and add. Okay, so for partial z partial s, that's going to be equal to 2x plus y times 1 plus x plus 2y times t. And then we can substitute for x and y back in terms of s and t. So another way to write this is going to be 2s plus t plus st plus t, s plus t plus 2st. And I'm sure if we wanted to, we could distribute collect like terms, make it look a little bit better, but I think that's fine for what we need. Now, in the same vein, we need to now find partial z partial t. All right? So if we find that, we're going to do the exact same thing. We're going to start out by finding partial z partial x, which we already know. That's 2x plus y. And then we also now need to find partial x with partial t, not partial x. S is last time. All right, so this is 2x plus y. And then we're going to have partial x partial t, which is 1 again. All right, so if we take the derivative of s plus t, that's just 1. Partial z partial y is going to be x plus 2y, and we just found that anyway, so we could just reuse it from over there. And then finally, partial y partial t is going to be s this time. Right? And again, we're just looking over here. Partial of t is 1, s is a coefficient, so it just comes down. And so now if we need partial z partial t, then that's going to be equal to 2xy times 1, or 2x plus y times 1, excuse me, plus x plus 2y times s. And just like we did before, if we want to go ahead and write the parameterization into a single term, or into our s and t, and get rid of the x and the y, we can write this as 2 quantity s plus t plus st plus s plus t plus 2st times s. And again, all I did was I just substituted for x, for y, for x, for y. Right? Again, we could distribute if we wanted to and collect like terms. And this one, just to say we did it once, we can. So we have 2s and s is 3s. We have 2t and t is 3t. I'm sorry, we can't do that. I forgot that there's an s out here. Apologies. So we'll end up with s squared. So we'll just distribute really quick. So we have 2s, 2t. We have an st, and then we have an st right here. So we're going to have 2 st's. And then we have s squared, and then we have 2s squared t. All right, so just to say that we've done it once, we've done it once. All right, now, just one second example, just to make sure that we see two of these to reinforce. Now we have sine x tan y as our xy, and we have the parameterization x equals 3s plus t, y equals s minus t. All right, so just like we did before, let's start by finding partial z partial x, and that's going to be cos x tan y. And since let's start out by finding partial z partial s. Partial x partial s is just going to be 3. Nice and easy. Partial z partial y is going to be sine x sec square y. And finally, partial, and by the way, this was partial x partial s. This is partial y partial s is going to be 1. And so to find partial z partial s, we're just going to throw all that together. And that's going to be equal to cos x tan y times 3. All right, so just like we did before, we're going to multiply, and then we're going to add and multiply that. So that's going to be sine x, continuing on the next line, sec square y times 1. If we wanted to, of course, we could back substitute, but let's just not do that because we've already done it a couple of times already. Let's see if we can find partial z partial t. And essentially, we can just borrow partial z partial x, partial z partial y. So partial z partial x, partial z partial y are cos x tan y and sine x sec square y. And this time we need partial x partial t, which is going to be equal to 1. And then partial y partial t is equal to negative 1. Right? And then finally we can just multiply. And if we multiply together, partial z partial t is going to be equal to cos x y tan, or cos x tan y times 1 plus, and we can actually make it a minus because of the minus 1 here, minus sine x sec square y. All right, and that should be good. All right, so now we've seen a couple examples of being able to take the partials of these sort of multivariable functions that have multivariable parameterizations as well as single parameterizations. In the last two videos within this section, we're going to take a look at why we would ever want to do this sort of thing. In other words, what's the benefit of this?